The International Academy of Wood Science runs an international competition for the best PhD thesis and awards 3 medals to the top 3 winners. Dr. Dvoracek won the 3rd place of the 2022 International Academy of Wood Science PhD award competition. He's currently a senior researcher with Wood K+ in Tulln, Austria. And his presentation today is about how to measure and predict wood cutting force precisely, with a question mark at the end. So I think he is online, and he will be available to answer any questions at the end of the presentation. Thank you.
Hello and welcome to my presentation at this symposium. My name is Ondrej Dvoracek. I won 3rd place in the doctoral award of the International Academy of Wood Science. Therefore, I've got invited to give a presentation about the research I've done during my PhD thesis. Today, I want to give you an overview of the measuring and predicting of cutting forces. Last years, I was employed as a researcher at the Wood Research Center Wood K+ in Austria. And at the same time, I joined the Doctoral School of Mechanical Engineering at the Technical University in Graz, also in Austria. During that, I've had the opportunity to work on several projects with many different partners, universities, and companies from several countries. I'm very thankful for the funding I've got for my research from the Austrian funding agency, the European Union, as well as local government. The question I was concerned about during last years was how can we measure and predict forces precisely. My today's presentation consists of 4 parts. The first is focused on wood cutting. I'm going to first express the motivation to the research. To conduct it, it was necessary to develop a new test setup. Then I will present the results of the cutting analysis. And finally, I will show you the established force prediction model. Wood is amazing, 100% natural, renewable and beautiful material. Especially now, our planet has limited resources in contrast to increasing demand. When the wood becomes waste, it can simply fertilize new plants. We can simply regrow it. Due to the reasons, wood is a perfect material for engineering purposes. The problem for our engineer is a very unpredictable material due to natural phenomenon. When I focus directly on cutting, what does influence the cutting? Standard parameters as for metallic materials: rake angle, chip thickness, cutting velocity. But furthermore, there are these influences from natural material. For example, moisture content. Wood is usually full of water. Wood is also a fibrous material, therefore, according to the cutting direction, the interaction changes as well as the disintegration mechanism. During common used sawing, the cutting edge goes through multiple wood layers of different densities and mechanical properties. For the research, it was necessary to develop a test device. This unique device works on principle of rotor arm. The rotor arm reaches an angular speed of up to 442 rotates per minute. Due to the rotor arm diameter of 4 meters, the movement of its end can be considered linear. That corresponds to the tangle shell cutting velocity of 93 meters per second. The whole device stands in the laboratory in Tulln, in Austria. A wooden sample is during examination placed on the end of the rotor arm. For lowering the initial impact, wood is placed between 2 polyurethane blocks. The knife is placed oppositely on the precise 3D quartz force sensor. Where the rotor arm reaches the knife, the cut occurs. Single cut per examination is conducted. It eliminates the influence of the previous cut. The combination of mentioned test parameters opens the unique possibility to investigate wood cutting. The stand-alone cut at this speed has never been performed before. Furthermore, the linearity approximation enables better insight into the process. Then I evaluated the device and used the device to acquire data about hardwood cutting. The main set of tests was performed on 6 different species. Samples were examined at 9 cutting velocities ranging from 5 to 80 meters per second at many different chip thicknesses from 0 millimeters touching the surface without splitting to 0.5 millimeters. And at the 5 different cutting fiber angles from along, it means 0 degrees, to across the wood grain, 90 degrees. Samples are climatized to 6 different moisture content levels from 0%, which means completely dry, to over saturated samples. So finally we got the data that were trustable. Original data are yellow and corrected data are gray. From the experiment record, just the cutting process was chosen. It's highlighted in red color. Before and after, it's the cutting of polyurethane blocks. From this acquisition, the mean peak force was evaluated. The first relation I want to show you is force dependence on the cutting and cut chip thickness. We can see the graph for 3 different velocities. Similarly to the literature, the force is non-zero when you reach limitly zero chip thickness. This is due to the friction component of the force. The intention is to point to the value of about 2 newtons per millimeter. Interestingly, at all speeds, this is a very similar value. In contrast to the literature, the progress is more or less exponential at speed of 10 meters per second, and it gets less curved at almost linear at speed of 80 meters per second. On these graphs, you can see how force depends on the cutting velocity. Very interestingly, the cutting force is not the lowest when cutting with the lowest speed. It's usually the lowest at around 20 meters per second. In the contrast to the study of Kimura, who found out the lowest speed at around 40 meters per second. On the right side, we can see the results of saturated samples. This was the exception. The trend is almost linear. It's probably because the wood is full of water that serves as a lubricant. A big help in the evaluation was the high-speed camera. In the recordings, you can see the wood and the knife. The cutting velocity is in this direction. On the previous slide, we saw the difference between cutting and different velocities. Here you can see the reason why the forces are different values at different speeds. It's so-called pre-splitting. It means that the crack propagates in front of the tip of the knife. I will show you 2 pictures focused on the surrounding of the tip. At low speeds, the pre-splitting crack is significantly longer than at speed of 80 meters per second. At the speed of 20 meters per second, the knife velocity and crack propagation's velocity are similar. That helps the knife go through the material with the least resistance. These relations I've recorded also for different wood species. It's measured for speed from 20 to 40 meters per second. The highest cutting forces requires Robinia and beech. The lowest is Paulownia. It is not surprising that it corresponds with density. Those are average density of the sample. When I standardize it, the data looks like this. Robinia and beech needs very low force to be cut, but with increasing speed it grows rapidly. Other species keep more uniform cutting force for all cutting speeds. Finally, almost 5,000 measured data that I presented until now were collected and incorporated into the prediction model. The first part of the prediction model is the equation in the form of trivariate cubic polynomial, including dependent variables of moisture content, cutting fiber angle, and cutting velocity. So by multiple application of least square method, the parameters were found. Then the evaluation matched the measured data with predicted coefficient of determination of 0.88. The standard deviation between measured and predicted values is little over 1 Newton per millimeter. The model contains more paths that need to be connected. It's done by their common plane of parameters to increase the number of variables. Furthermore, I added to equation also multiplication according to cutting width and correction in accordance with the wood density. Similar to that, I created the cutting model for other species. Interestingly, you can observe that Paulovnia and spruce is not that strongly dependent on the cutting fiber angle, especially like the upper tree species. Interestingly, Paulovnia keeps the cutting force very uniform for all parameters set. And how can we use this prediction model? I and the co-authors of the publication inserted this model into the web calculator. You can find it at the address ondrejdvoracek.github.io. You insert a moisture content, cutting fiber angle, cutting velocity, density, uncut chip thickness, and cutting width, and it calculates the cutting force according to the model. Now let me conclude the research I have done during last years. I've developed a novel test trick that can approximate linear cutting and measure cutting forces while speeds that were not measured before. I optimized the device settings, and what couldn't be optimized I investigated and described. Therefore, with this device I achieved reproducible results. I performed extensive experimental research where I measured forces for known parameters. Sometimes also high-speed cameras recorded the cutting process. And finally, I developed a prediction model for the many parameters involved. If you want to know more about the device, you can watch the video under this QR code. Finally, I want to thank you all for your attention, and I appreciate the invitation to this symposium. If you have any questions or think that anything I've said might help you with your research, contact me at my email address and I will get back to you. Enjoy the rest of the symposium and see you next time.
Hey, thank you, Dr. Dvoracek. I think he's also online with us today. So if there is any specific question for him, please go ahead.
Hello, I made it also to join, so please, I'm ready to answer your questions.
Okay, there is a question about, is this technology transferred to industries?
Yes, it was done in cooperation with industries. With industry, for example, with certain factories who are producing cutting knives. And we have also communicated with other researchers within our region, because it was over border project. So definitely yes, it was. There were already made some tests on this device for certain sawmill blades. So definitely there is possibility to do measurements for for many companies.
Okay, thank you. Are there any other questions?
So my question is brief. And what was the highest density, the wood density have you ever tested?
It was around 600 kilograms per cubic meter.
Thank you.
A little bit over 600. So, and I think there is still a gap, because this is the biggest restriction in this is the rigidity of the test stand, and I made the test stand very rigid, and therefore I think we can go with densities even higher. Also, I can imagine this stand being used for some composite materials up to 1,200 kilograms per cubic meter.
I see. Thank you.
Thank you very much.